Yeah, so for the midterm, Codathon is only going to be looking at the text file that you have created to see what the output is. For the screen, I guess you could render whatever you feel like as long as the text is fine and the game is playable and makes sense. Anything else? Okay, so we're actually going to start C++ today. Yay! Don't worry, things get better once we get to C++. It's not as nice as Python, but it's better than C. So C is a subset of C++, 99% true. Pretty much everything you know in C also works in C++, with some minor differences. So bool is now a built-in type. You don't have to include stdbool.h anymore, which is pretty cool. When you compile, you use G++ instead of GCC. You still use the same options. We'll be talking about the 2014 standard here in this class. They're currently working on or have pretty much finished the 2018, but I haven't learned that yet to see what's different. So that's why I'm still doing 2014. When you compile, you can say the standard equals C++ 14 to make sure you compile for that. When you're doing your CMake lists, there's an option to specify in there, or when you're creating your project, you can do like CMake set CXX standard to be like 11 or 14 or 18 for the particular year. We'll go over more examples of CMake stuff on discussion next week. The extension for CPP files is .cpp. The extension for header files is .h, and sometimes it's .hpp. You can still include C library code and still use all that same stuff that you've done before, except the name of the file has changed. So instead of including my C library.h, you include C, whatever your C library name is. So instead of stdlib.h, it's C stdlib. Instead of math.h, C math. Instead of stdio, C stdio. Hopefully that makes sense. The reason for this is to help differentiate between what's pure C and what's C++. Files you can still create are included like normal. So if you have a cool header file called coolheader.h, you'd still do #include coolheader.h. For doing I/O, you can still use printf and scanf. But the more common thing to do is to read from or write to read from cout or write to read from cin and write to cout. Both of them are located inside IO stream, and so if you want to print, it's std : cout, and then you separate them by this double arrow sign, and then the value, the expressions, and then will be transformed into the correct string representations and then printed to the screen. If you want to do a new line, it's std : endl. You can also do /new line, works as well. The syntax for reading is cin, variable 1, variable 2, variable 3, assuming you wanted the variables to be separated by a white space character. And you can think about like the arrows are telling you like whether it should be coming from input or going to the output, right? These variables are coming from standard in into var1, var2, var3. The values over here from expression 1, expression 2, expression 3 are being written out to the screen. I'll show you some examples of this in a little bit. One cool thing about C++ is that functions no longer have to have unique names. They have to have what's a unique signature. And a signature is pretty much the name and the return type and the orderings of the arguments. So multiple functions can have the same name as long as they have the same or have different signatures, and this is called function overloading. There are some rules for looking up which function is supposed to be called at a particular point. The rules are rather complicated, and you can see some details here. But the first thing that's going to try to do is find a function with that name. Then after it finds a function with that name, it's going to look for a function that has the same number of arguments. That's what you called it with. And then it's going to look for the one that has the closest match in terms of argument types to call. That has the same number of arguments. If it can't find one with an exact match, it'll attempt to implicitly convert the arguments, if possible, to the one that you called. So here's some examples. So this function's like int foo, and it just prints foo. We have double foo, which doesn't quite work because double and int are too close. They're too easy to implicitly convert to each other. It can't be here. Then we have int foo. This one takes a character and an integer. This one takes an integer and a character. And then foo char c int int I and j. It will then, call it with those values. So we have foo, we'll call ifoo. That's the one that matches. If we have a12, it's going to call the one that probably matches with character integer. 45x integer character. A23, call the one with 3 arguments. 123 is also going to call the one with 3 arguments because that matches. Oops. But if we have foo 2.5, 12, and foo 10, 2.0, which of these do you think is going to be called? I know, right? It's confusing, and hopefully you never end up in this situation. Yeah. So the question is there a reason why we want to give different functions the same name? Yes, because it makes it really nice if you have a function, for example, if you think about curses, right? There's a function for writing a character. There's a function for moving and writing a character. It would probably be nice if you just had a function called add character, one that just took a character and would write the character where you're currently at, and one that took 3 arguments, the row and the column, and the character that you want to write and moves there. So it just provides a bit of a nicer interface instead of having to have these unique names everywhere. Let me go find that example. Function overloading. So we'll wait for the CMake project to hopefully load quickly. And you can see that we call it, oops. So if we tried doing what was suggested on the screen, it doesn't actually work. So if I try to do foo with some, come on. So you notice it's like, hey, this call is ambiguous. I don't know which one to call. So what you'd have to do for these ambiguous ones is you have to cast them. I'm really slow because it's still updating those symbols. So you're getting a little bit of a preview of the different way of casting. So static cast means change the value in the parentheses to the value inside the triangular brackets. So cast 10 to a character, cast 11 to an integer, and then go and call that function. So C now has enough information here to know, like, hey, you want character integer function called. This one, I want integer character called. So you specify the ambiguity by casting to the appropriate type so that it knows which one you really want to have run. Yeah. Oh, over here? Yeah, I still have to. That's function overloading. It's really nice. So the way that like C++ resolves this behind the scenes is kind of it's done through namemangling. So externally you'll have different function name, or the same function name, but internally it's going to go change those same functions with different signatures to have unique names inside. So for example, if we had like int foo integer, it might internally rename that function to be I foo I, returns an integer and accepts 2 integers. Or char foo char int might be c foo ci, so that we know which one to call then. That's internal stuff if you're interested about it, but it doesn't actually affect you being able to program in C++. So functions can now have default parameters just like they can in Python. So when you want the default parameters, it's just like you do in Python. You know, when you declare your function, it equals some value, But unlike in Python, you can't just specify you can't just override a default value for a particular default parameter. They have to be listed in order. So here you can see I have a required argument, a default argument because it has a default value, a default argument because it has a default value. The default values, again, just like in Python, they have to come after the required arguments. And if you don't want to give the default, you don't want to give a value for the default parameter, the default is obviously going to be used. And then if you want to give a default argument a different value than the one that it defaults to, you can specify it, but you kind of have to go in order. So if I want to specify default argument 2, I have to specify default argument 1 as well. Whereas in Python, you could say like default argument name or default argument 2 equals new value and say only that one. So kind of sucks. So here you might say num1, num2, right? They're both defaults. So if we just do sub, it's calling it with num1 equals 20, num2 equals 10. If we do sub with 40, that's going to change num1 to be 40. 0 and 5 would be 0 minus 5 to get negative 5. This you could do in Python, can't do in C++, unfortunately. So if you wanted to call it with given the default value for num1 is 20, and then your second argument had the value 5, you have to say 25. Kind of blows. Also, you might not like types, and so C++ has a way of figuring out what the type is for you in certain situations. It's called auto. You can still add any additional modifiers you want, like const or pointer. So you can say auto pointer or const auto or static auto, like static const auto, whatever. You can add them all in. When you create a variable whose type is auto, you actually have to do an assignment to it, because auto doesn't mean that it's going to automatically change to be whatever the things that you assign to it. The types are still statically typed. This just means, compiler, please figure out what the type of this thing is for me and put that type in there. Because again, if you just said like auto X, C++ wouldn't know what that type is, and so it'll complain at you. I recommend using auto when you have a type name that's really long and you don't want to keep typing it out over and over again. That's also a case where you could use a type def to shorten it. It also can be really useful because you can specify the return value of a function as auto as well. You can't specify parameters as auto, but the return value and any local variables you can specify as auto, because the compiler will deduce the return value based on what you say to return. But again, all your returns would have to return the same type of thing for that to work, right? You couldn't say like return char one time, return int another time, return double another time. The compiler's gonna be like, no, all the return types have to be the same. But what could be nice is if you use auto in a lot of places and you decide to change the internal type, you don't have to go everywhere else and update that type. Auto will figure it out for you. For me personally, like auto kind of like messes with me. It's nice not having to write it because I come from a statically typed background, but then I'm also kind of confused because I'm like, I like having the type there to know what it does. I'm kind of like a mixed bag on it. So this is just heads up. So if we do like auto x equals 5, since 5 is an integer, x's type is an integer. Auto num equals 2.4. Num is a float because I specifically set a float by adding the f there. So num is a float. Truth equals false will be a bool. Auto big num equals 35.78 lf, long float, so it's a double. Const auto fixed equals 12, it's a const integer. If you just do auto something, that's going to be a compiler error. Any questions so far? Yeah. So like you want to put auto inside the struct for one of its members? So I guess your question is like, can you use auto for user-defined types? You can, right? So if you had some function that's like that was like called make matrix, right? And it returned an instance of a matrix struct, right? You could say auto m equals make matrix, and then auto would be deduced to be type matrix. Or even in that function, since it returns a matrix, you could say auto make matrix, num rows, num columns, and then inside your code you might say I have a matrix m, and at the bottom you return m. Then again, C++ would be able to deduce that the return type of this function is of type matrix. And so yes, it does work with user-defined types. But if you're asking, can I have like a matrix, type def struct matrix, right? Auto num rows, num columns. No, because I don't know what the type of num rows and num columns inside the matrix is supposed to be. You'd have to say int num rows, num columns. Anything else? Yeah. So you cannot use auto to define the types of parameters, because how is C++ supposed to figure out what you want? Right? It has to have some value being there to deduce what the type of that expression is. So parameters cannot be auto. You could probably say like auto x square brackets equals curly bracket 1, 2, 3, 4, and then it would deduce it that the type of auto is supposed to be int. So you have int x square bracket 1, 2, 3, 4. Like, so it actually like size 5. But yes, it could be used in that situation. And one of these things is like, can it be used here? Can it be used there? Just try it out, right? Make a little example, see if it will compile or not. And if it doesn't, then probably not. If it does, it should be fine. Again, it can also be used for the return value of function. This function returns a constant int, so auto num1 equals 5 means num1, or auto is going to be expanded here to be const integer. If I do const auto num2 equals 5, then the type of auto just gets expanded to int to fill in the rest. So dynamically allocating memory, everybody's favorite thing to do. There's a new syntax that we use. We use the new keyword here in C++. You can still use malloc if you want. The difference between like new and malloc is malloc just makes space. New makes the space and initializes it based on the constructor, which we'll talk about constructors later. And it's going to return a pointer to that type. Any space that you create using new, you need to delete using delete. It's going to be an undefined behavior if you create space with malloc and free it using delete, or if you create space with malloc and free it using delete. Right? So if mallocs have to be freed by free, space created by new has to be deleted by delete. So just match them up. One of the downsides about new is that there's no equivalent to realloc, so you can't just change the size of something. If you wanted to, you'd have to like make a new copy that's the new size, copy over all the old values, and then delete the original and return the pointer to that. You can also make space for arrays by saying new type amount, and it will make space for that many things. And then when you want to delete that array, you would say delete square brackets and then that array. Yeah, and in C you can delete classes assuming the space has been created by new. Or again, even with a struct, right? If you have a struct that's created by new, you would delete it via delete. So, some simple examples of doing the creation and deletion using new. The only one I think that's somewhat interesting is the creating the space for the array and then deleting the array. You have to use the delete square brackets to delete all the elements. Yeah. I think it's undefined behavior if you leave off the square brackets. Because it'll try to it'll delete it, maybe just like the first element and leave the rest. Or it might cause other undefined behavior. So in addition to const, right? Const means you're not going to modify that variable. There's also a new keyword called const expression. If you're using const expression, if it's known at compile time, the value will be substituted in. And some functions can also be defined as returning a const expression if you know the values at compile time. This would allow you to call your functions in certain areas with like when you're doing templating to get like the sizes of things using the const expression where const can't be used. So pretty much now use like const expression. You use const where keep using const. We probably won't deal with const expression that much. Any expression that's used as const expression can be used in a switch statement. And const expression can be used to allow the compiler to make some more optimizations. So no longer use null, use null pointer. Null is really just a pound define that has the value 0. So anywhere before you were saying null, you're really just saying 0. This is very type unsafe because I can have an integer x equals null. That's totally fine. Probably not what I intended to do. So instead, use null pointer. Null pointer has a type of type null pointer. Kind of weird. but it will help you. It's a lot more type safe. So int x equals null, that's legal. Int y equals null pointer, can't do that because you have an integer on the right hand side and a type of null pointer on the right. Any pointer though can point to null pointer. So I have an integer pointer p, that can be equal to null pointer. Char pointer x, that can be equal to null pointer. Also, we have references, which are really cool. We'll show some examples in a second. References are really similar to pointers, and they're like ninja pointers, so that makes them cooler and better to use. And so what they are, they're basically pointers that don't have to be dereferenced. And they're always going to be pointing to something, for the most part. There are ways of breaking that to make it not happen. Another way of thinking about it is that a reference is just another name for that variable. And you're actually going to go to where that variable's at and modify it. One thing about references is that once a reference is assigned to refer to something, you can't make it refer to anything else. The syntax for it uses the ampersand, so it can get confusing using like the address of and a reference to. So the address of is going to be, the ampersand will be used as the type. So you might have type reference var name equals expression. This makes the var always refer to expression. A lot of functions will ask for a const reference, and most of the functions you should be writing should accept references because it's a lot faster to pass around the references, which again are essentially just pointers, than to pass around and copies of the object. Because copying the object takes time, especially if the object's very big. If you're not planning on changing the value of that variable in your function, though, pass it a const reference to guarantee that the user that's calling this function, you won't modify it, and you get the speed up of being able to pass it faster. So here, right, we have a function set to 10, integer reference x. So x is just going to be another name for the guy that's passed in. We also have an integer plus 5 const integer reference y equals return y plus 5. So over here on the right, we have a equals 12, integer reference a ref equals a. Again, when you create the reference, it has to be assigned to refer to something. So now aref is just going to be another name for a. So any modifications I do to aref also show up as being done to a as well, because they're referring to the same location in memory. So if I do aref equals 7, a also gets set to 7, because aref is another name for a. If I set to 10 a's value is now 10. If I do aref equals plus 5a, a is now 15. Change it back to 10. This thing down here would be illegal because you have a double reference d, and that is d is referring to, I don't know, so it's illegal. So remember how we had functions before and we would pass pointers to those functions to be able to modify the arguments? Now if that's your goal is to modify your argument, pass a reference to it and you don't have to dereference it anymore. The question is, could you do double reference d equals null pointer? No, you can't, because d has to refer to something that exists, right? So we'll talk in a second. There are times where you want to use references and there are times where you want to use pointers. We'll talk about that in a second, but the main rule is you pretty much want to prefer always using references because they're always going to refer to something. You don't have to worry about null pointers. You'll use pointers if you need to have like a nullability. If you need to be able to check that you're not pointing at anything, there's nothing there, then you have to use pointers. If your pointer is always going to be pointing to something, use a reference instead. Anything else? Reference. So you can't make a reference to a reference. So you can't have like an integer reference, but you can have an integer reference equal to another reference. Right? So I could do like integer reference bref equals aref. That's fine. They're referring to the same integer a now. But I couldn't have a reference for my reference. Someone had a question? Yeah. Yes, you can make struct like references to user-defined types. You can. So the question is, if we were like inside one of these functions, like set to 10, and set to 10 called some other function, right? Would I be passing in like a in our example, the original a that we had back here? The answer to that question depends on what did your function accept. right? If that function accepts a reference, then yes, it's referring back to A, right? But if the function just accepts an integer, then it's going to make a copy of the value.
Next function then passes in our double last one. In that case, you have to reference next function also last one.
Instead of having like lots of pointers. So like in general, like for the read lines function that we had right now for our homework, right? We had like the triple pointer, right? So what we would have done in C++ instead is we probably would have had a char pointer reference. They don't have to do that extra dereferencing in parentheses everywhere, right? You guys all had to keep like dereference lines in parentheses everywhere. Now you can just say lines and it works. Which is nice, right? Because I really wanted to be able to refer to that double pointer right back in main. That was my whole goal of passing the triple pointer to it. And this gives you a lot nicer syntax to it.
Modify the line and having to return a char.
So in that particular example, if you had a function that read a line, it would still probably make the most sense for that function to return a char pointer. If you wanted to modify a char pointer that was passed in, you would pass in char pointer reference to the line to fill in. And that would totally work. So the examples here, yeah. So pretty much like everywhere an integer is accepted, an integer reference is also accepted. The big difference between like when you declare, like the big difference is like when you declare a variable of type integer reference and when you have a function accept a type of integer reference. Because if you just have a function that accepts something of type int, right, I get a copy of the value that's passed in. If my function now has a type of integer reference, it refers to the original, right? So if I do modifications to that argument inside the function, I modify the thing that was passed in. Whereas in the first one, since I have a copy of it, if I do modifications to the copy, well, I change the copy. Correct. Everything that accepts an integer is also happy to take an integer reference. But so if you pass an integer reference to something that requires an integer, it's just going to take a copy of that value, just like it would if you passed it a normal integer. Yes, you can do auto reference, and you'll see that later on. So you can have like auto reference equals x, right? Now you are a reference to whatever x's type is. So remember, like the reference is just another name for the struct, right? So you still do struct dot, reference dot, right? It's the same thing. It's just another name for it. There's no special syntax with references except for declaring them. Everything else is like you have that integer, but you have the real deal, not the copy if you're inside a function. So over here, right, here's a pointer version of swap. We want to swap two values. So I need to take in pointers to integers to be able to change their values because I need to be able to go to those locations memory to modify them. So swap is not that interesting. But here, if I have references, right, notice I don't have to dereference them anymore because I have the original variables in there. So again, like if your goal is to modify the thing that you're being passed in, take a reference to the thing, right? Don't take pointers to it anymore. So like here's a pointer version of insert that we've seen before, right? So I have the value that I want to put in, the position that I want to put it at. I have to take a double pointer to the array of my array of integers because I need to modify it inside the function. Down here, star AR equals, right? Go to that location memory so I can do the resize. and then I need a pointer to len to be able to modify it. So right, we increase len by 1, then we reallocate the space, right, by making sure that we dereference everywhere, just like you guys were doing inside of the read lines code. Notice like there's the parentheses dereference everywhere. If we go back to the reference version though, I have a constant integer reference to a value, a constant integer reference to the position. That's not really that important, but I have an integer pointer reference, a reference to that integer pointer, an integer reference for length. I have a reference to that length. So now, notice there's no more dereferencing on array everywhere. It cleans up the syntax quite a bit and helps you prevent from making mistakes. Yeah. So I don't have an integer pointer to a reference. I have a reference to an integer pointer. So you can, a lot of times with like the references and stuff, you read it backwards. I have a reference to a pointer to an integer. Or down here, I have a pointer to an integer. You read right from left instead of left to right. But there's a big difference between having an integer pointer, or a reference to an integer pointer, and a pointer to an integer reference. I don't think you can have the second one in terms of a type. Do you guys have any questions on using the references here? I know it gives like another name for like the ampersand. That makes things a little bit confusing for people because it can show up in another place, right? Because like if we see this right here, ampersand AR, ampersand len, am I saying I want a reference to it, or am I saying something else? I want the address of it, right? So these are going to give me pointers to the things, which sometimes gets people confused when we have our types up here declared as something like integer reference. They're like, oh, is that a pointer? Is that its address? No, it's a reference to the thing. It just happens to use the same syntax. And again, use of the static cast, which we'll talk about more later. And then printing out the values. So we said that references always refer to something, right? Whereas a pointer, it could point to null, point to nothing. But sometimes you have something what's called the dangling reference problem, and this is just like a problem in your program. You made a mistake. So there are times where a reference could refer to memory that's no longer in existence. Called the dangling reference problem, and this normally happens when you dynamically allocate space to something, create a reference to that space, then delete that space, then attempt to use the reference. There's also really no way to detect when this happens, but you'll probably get a seg fault or some other weird behavior. So what this would look like is we create a new integer dynamically. I create a reference to the integer, all fine. I can assign it to 10, right? That's going to go change that integer that we've created, a star x to be 10. I delete x, it's now gone, but notice my reference is still referring to that same location of memory that I just deleted. So doing something like this now causes problems. I have a dangling reference right after I delete what I'm referring to. So watch out for this. Questions here? Yeah. So the question is, shouldn't it be integer pointer ampersand xref equals x? So you could do that if you wanted a reference to the integer pointer. But I don't want a reference to the integer pointer. I want a reference to the integer that it's being pointed to. But yeah, you could take out this star here and then have integer pointer reference, and that would be a legal statement, but not the example that I want to be showing here. Anything else? Yeah.
So, the reference variables.
References don't really take up space. They're just another name for it. It's kind of like a pointer. It's like a hidden pointer for the most part. No. But if you can ask for the address of a reference, and it will give you the address of the thing it refers to. So back here, right? If I ask, like, what's the address of a ref? It's the address of A. Does that make sense? Reference doesn't. Correct. Reference does not have an address. It just is another name to refer to that location of memory by. Any other questions? Okay. So C++ has 3 different types of casting. They're the static, dynamic, and reinterpret cast. So I recommend using the static cast for doing the type of casting that we've been doing up until now. It will attempt, if you do static cast BA, it will attempt to convert A to type B, if there exists a conversion to it. If it's not possible to convert A's to B's, the compiler will raise an error about this, and it won't compile, which is really nice. The dynamic cast will attempt to, again, change A to B, but it behaves differently if the things that you're trying to cast are pointers. If A and B are pointers or references, and this becomes a lot later when we get to polymorphism, a downcast or a sidecast, the dynamic cast checks at runtime to see if A really is a reference of, it really is an instance of B. So like, are you really that thing? And if it is, the cast will be successful. We're just not going to be using dynamic cast right now. It's just being pointed out. But if it's not, if you're trying to cast pointers, you'll get the null pointer back. If you're trying to do a cast on the reference, it will give you an exception and your program will crash. There are ways of catching that exception, though, and doing something different with it, which we'll talk about later on. And there's also reinterpret cast, and it's going to be like, hey, treat A as type B, regardless of what it is. So this one's like really unsafe to do unless you really know what you're doing. So don't use that one for right now. So for right now, just use static casting as opposed to the C-style casting we were doing before. And then once we get to inheritance and polymorphism, we'll talk about dynamic cast. And we'll never use reinterpret cast in this class. So with a union in C, that generally makes space for one of some multiple variables. So you might have like union integer A, integer B, integer C, double X or something. So only like A or B or C or X could exist in that space in memory at once, which is very different from changing like, hey, treat this type as this other type. So casting, seen it, went too crazy. There's also namespaces, which are great, but a lot of beginner programmers hate namespaces to begin with, because they're like, why do I have to type all this extra crap all the time to get things to work? And so what namespaces are there ways to gather related concepts into one logical area. This namespace might extend across multiple files. This is generally really useful for like when you're using projects or other libraries, and you want to make sure that your code doesn't interfere with somebody else's code. The whole point of namespaces is to prevent name collisions. So it really sucks if someone just happens to use the same name as your function, and now you can no longer use that function name because some other library that you're using is using that name or happens to have that same signature. And so namespaces prevent this problem. The way that namespace works is you say namespace, whatever you want to name your namespace, and then put inside curly brackets stuff that belongs to it. And you can do this multiple times throughout the file. So you might do it like this in like file 1 and file 2 and file 3. And as long as they all have the same name for the namespace, they'll all be inside the same logical namespace despite being separated across multiple files. Within that namespace, you can refer to any of your object or any of your like your functions or any of the members of that namespace directly by their name. If somebody is in a different namespace, you have to go say what namespace do you want to call that function from. So if I want to call some function foo and it's in namespace Bob and I'm not in the Bob namespace, I do Bob : foo to call Bob's foo, which we'll see some examples in a second. And code that you don't place in any namespace is placed into the global namespace. The way to access the global namespace is : function name, if you want to be specific about it. There's also some like namespace like resolution. So it will look inside your current namespace for like a function whose name matches that. If it doesn't find a function of that name, it will look inside the enclosing namespace. If it doesn't find a match there, it'll look inside the next namespace, up and up and up until it finally reaches the global namespace. And if it doesn't find something there, you'll get a compile error. But if it finds something along the way that matches the signature, it'll use that one instead. So here's some examples. Here I create a Bob namespace, and I have two functions inside of it. And so here I have a foo, and I have a foo2. Then I also have a John namespace. John's foo prints John foo, and then foo2 calls foo foo. Right? So if we call Bob's foo, Bob colon foo, we'll call Bob's foo. Call John's foo. And then we'll call John's foo as well. And then here we can create the namespace again, reestablish it, namespace Bob, and now I've put a third function inside Bob, which we'll then call foo and then foo2. Open. So while that gets loaded up, again, the namespaces can be nested. So, right, you might have parent namespace, has a child namespace, has a grandchild namespace. And if you want to refer to that particular function, foo, inside the grandchild, parent, child, grandchild, foo, to get all the way down there. But again, if you were inside the child namespace, you could just say foo and be done with it. And again, the resolution for the names they're going from the most enclosing namespace on up. So let's go back here. So I have a couple of different files over here. This keeps building my symbols. So if we're splitting across multiple files, here's one way of doing it. So I have namespace space 1, and it has two functions, fun1 and fun2, defined inside space 1. Over here in space1.cpp, if I want to refer to those functions and doing those definitions, space1 : fun1. This is the definition for function 1 inside namespace 1. Function 2 inside namespace 1. Space 2.h has space 2 and functions 1, 2, 3, and 7. Notice that space 1 and space 2 have some functions with the exact same signature, right? But this is fine now because they're enclosed inside separate namespaces. So there's not going to be any name conflicts. And then again, we define the functions. So fun1 will just say fun1, fun2 will just print out fun2, then call fun1. Fun3 will call fun3, and then here, since this function is defined inside namespace 2, if I want to call namespace 1's function 1, I have to say space 1 : function 1, right? Whereas up here, and I say function 1, which function 1 am I going to call? The function 1 in namespace 1 or the function 1 in namespace 2? In namespace 1? In namespace 2? In namespace 2, because you can see this function fun2 is inside what namespace? Space 2, right? And so we're going to look inside our namespace first for our function 1. So we call this one up here. And then this one is function 7. Over here, you can see that I continued namespace 1. It has a 3 and a 4, but defined a different file. And instead of prefacing each one of the functions with the name of its namespace, what you can do is do namespace space 1 and then put the definitions inside there as well. So now I don't have to say space 1 : fun3, because right now I'm saying I'm inside namespace, or inside the space 1 namespace. Correct. And there are ways of bringing the symbols from another namespace into your namespace, which we'll see in a second. It's using the using directive. So if I say like using namespace std, that says, hey, I want to be inside the std namespace. Bring all those symbols in. So instead of having to do std : cn, I could just do cn then. I'm going to discourage that practice though, because the whole point of namespaces is to prevent this name collision. And by using more namespaces inside your code, you increase the odds of a name collision happening. It may not be happening right now, but as people add code or edit code or things change, it increases the likelihood of that happening, which you want to avoid, right? If someone else changes a library and adds some function to it, you don't want your code to no longer stop working. Any other questions? So here's the example of the using keyword. So if I say using namespace space 2, this means I brought all the symbols from space 2 in. So if I just say like fun1 or fun2, I'm going to be calling space 2's function 1 or function 2 because I brought in their symbols using namespace space 2. Yeah. You can, but then there's the problem, right? Down here. If I do this, I'm going to start getting errors because I brought in all the symbols from space 2 and all the symbols from space 1 into my current namespace, right? But now space 1 defined a symbol called function 1. Space 2 defined a symbol called function 2. And now since there's two functions that have the name function 1, right, they conflict. And that's the name conflict that we're trying to avoid by using the namespaces, which is, again, why I recommend not using this using namespace directive. So these ones we'll call space 1's functions. These ones we'll call space 2's functions. And I will force you to use namespaces in your code too. So you get practice with it, because I know at the beginning, no one told me why this was important. And it's important if you want to write high quality code. You guys have any questions on namespaces, like why we use them? Yeah. So when I said using namespace space 2, the symbols that I brought in, what space were they placed into? Okay, so if I say using namespace space 2, and then I create some other function, my cool function, right? Is that function going to be placed inside the space 2 namespace? No, it won't. What the using directive does is it brings in the names from that namespace into your current space. So have you ever, like in Python, used the import directive? Right? You can say like import math, right? And then if you wanted to access the log function, right, you'd have to do like math.log. Right? But the other way of importing in Python is like from math import log, right? That brings log into your current namespace in Python. So now you can just say log. But if you had another function whose name was log, it just got overwritten by the math's log function, which is why it can be somewhat unsafe. So any function that I created in here, like main, for example, main is in the global namespace, not inside namespace 2, even if I move the using namespace line up here. That's a great question. Anything else about namespaces? Yeah. Oh, how would you stop using a namespace that you've already said you were using? I don't know if that's possible, but the answer that I can think of right now is don't use the using directive, right? If I didn't want to use the using directive here and I wanted to call space 2's functions, I would do space 2 : function name, right? And now it's very easy to disambiguate which one I'm actually calling. Space 1's or space 2's or whatever your namespace happens to be. So hold on one second. So the question is if we use the using namespace directive inside of a function, like what's the scope of the using directive? I believe it would be inside that function only. You would be using that new namespace, but I'm not 100% sure. My guess is it would only be for the scope of that function you would be using that namespace. You'd bring the symbols in. And as soon as the function ended, it wouldn't affect anything else. Okay, guys, I will see you in office or discussion in an hour.